to go? Okay, so the recorder is on, and I just want to kind of emphasize the value of this class, because I know, when I was a student, well, never mind, when I was a student, I never think that way either. But for some people, they take a task, they take a class because the class is required. Okay, it is part of the the degree, and they have to take the class. But when I teach a class, I don't want to teach a class just because these are the topics in the curriculum, and I have to cover a lot of the topics. I want you guys to get something out of this class that is actually practical. Okay, and the practical thing out of this class is to diagnose your C and C++ programs in a way that you were not able to do it before this class. That is the value. Because you can corrupt certain things on the stack and end up with a problem that you cannot explain if you do not understand the underlying implementation of C and C++. So unless you think that, well, I'm only going to program in PHP and Java, I will never program in C and C++ ever again, then you don't have to worry about the things that we are going to talk about. But how many of you, think that you might program in C or C++ in the future? Okay, well, then some of the topics that we'll be talking about is going to be helpful. Okay, so with that as a context, I'm going to move on. And here's your new homework assignment. It's not going to be that difficult. I know it looks really kind of nasty, but it's not. So we'll take a quick look at this homework assignment. And so let me switch to a terminal. I guess it's in my downloads folder. And that one's called Factorial. And inside the Factorial program, there's only one subroutine you have to do, and you have to do it in assembly. And guess what is the name of that subroutine?
Factorial.
Well, it's Factorial. Yes, exactly. So the first part of this source file is the code that you have to implement. That is in C code, the first part, the first 4 lines. And that's the subroutine that you have to implement. There are missing pieces that I have to update you, that you have to know first before you can do this homework assignment. So I'm going to give you the pieces first, and then we'll be able to get this homework assignment done. Okay, but before we worry about the assembly language implementation, is the C code clear enough that people can understand exactly what it means in C and just the logic of the subroutine itself? Okay, so I'm going to go over that a little bit, just from the expression. I can see that some people may not have seen this type of syntax a whole lot. Okay, so instead of using a conditional statement, I'm using a kind of special operator in C and C++. What is this called?
I think it's called the lambda operator.
Is it called a what?
The lambda operator?
The log?
Lambda?
Lambda?
I may be wrong on that. I think that's what it's called.
Yeah. Conditional, tertiary, operator. Yeah. So it's
That's it.
yeah, that's it. So basically what it is okay. So basically what it is a conditional statement in an expression. This is the condition. If this condition is true, this becomes the value of the entire expression. Otherwise, this becomes the entire expression. This becomes the value of the entire expression. Okay, is that okay so far? The first part, the part that is to the left-hand side of the question mark, is the condition. If the condition returns non-zero, then whatever is between the question mark and the colon becomes the value of the expression. If the condition is returning 0, then whatever is to the right-hand side of the colon becomes the value of the expression. So it's basically a conditional statement, except it is expressed as a single expression instead of a conditional statement where you have if, blah, 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 then this, and then else that. Okay? Okay, so once we understand that, then we know that there's a condition involved and there's a recursion involved here. Okay? The recursion is Factorial is invoking itself, it is calling itself. Okay? And let me just highlight the part that is recursive, which is right here. Okay. So that means in this particular case, unlike your previous homework assignment or the one that is due a few minutes ago, That one only requires you to return a value. This one requires you not only to return a value, but also to set up the stack to call a subroutine. Okay? And in fact, it is the very same subroutine that you're implementing at that time. Are we doing okay so far with those concepts? Okay. So what we'll do today is to look at various pieces of this particular program, I will demonstrate and test each piece individually, and then you guys will have to put everything together. Is that okay? All right, so the first thing we have to do is to understand how do we do multiplication, because there is a multiplication involved here. I am taking the result of the factorial of n minus 1 and multiply that to my own parameter n. Okay, so how do we do multiplication? So let's go ahead and take a look at a simpler program. I'll just call that mult.s, because the only purpose of this program is to illustrate how to do multiplication. To do multiplication, okay, I still need all the usual stuff here so that the program would link and actually run in GDB. So what I do is I'm going to say, let's just say, okay, let me in the comments, we'll just go ahead and say multiply, we'll just pick some constants here. 1,234 and 5,678. 5,678. I just want to multiply those two numbers and find out what is the product of those two numbers. Okay. So the first thing we have to do is to set up the registers. The first register that we have to set up is EAX. Okay. So we move one of the numbers into EAX, and then we can set up the other number in another register. So let's say 5678 is going to be set up or stored in EBX. So now we are ready to do the actual multiplication. The multiply instruction is not really like the addition or subtraction instruction, because this one has got an implicit operand. Okay, one of the operands or one of the registers involved in the multiplication is not mentioned by name. It is simply implied. So we'll take a look at the mul instruction. MULL is the name of the multiply long instruction. It only takes one operand, which doesn't make any sense at all, right? When you're trying to multiply numbers, you always multiply two numbers to become the product. It's just like when you're dealing with addition, you're adding two numbers. So how come the multiply instruction only has one single operand? And in this case, the only operand I have to specify is EBX. Well, that's because EAX is an implied operand. Multiply always assumes one of the operand is in EAX. So you only have to specify the second operand, the other number that you're trying to multiply. Is that okay so far? So EAX is already implied, and we just have to specify the other one. Okay. So just for interesting, side effects, what we'll do is we're going to put something into EDX. So we'll put, 0x ABCD into EDX for no particular reason. Well, I actually do have a reason, but I'm not going to explain it now. I will explain it later. And that's the entire program. And after this, I'm just going to exit this particular program, because we are done at this point. So this program, the only purpose of this program is to illustrate how to use the multiply instruction. And on top of that, some of the kind of tricky stuff that you have to worry about when you use the multiply instruction. And by the way, mul is unsigned to begin with. Multiplication, unlike subtraction or addition, is either signed or unsigned. There's one instruction for signed and one for unsigned. And if I remember correctly, mul is the unsigned version, but I can be wrong. Okay. Why do you think multiply is either signed or unsigned? You cannot apply to both. How do you multiply numbers?
Addition. Repeated addition.
It's a whole bunch of shifting operations, and also additions. Now, when you have shift operations, it is sign specific, because the way you sign extend a number depends on whether the number is signed or not. If a number is not signed, you only pad zeros on one side. On the other hand, if a number is signed, then you have to replicate the most significant digit several times in order to perform the shift operations. So that's why multiply is actually, you have to specify whether it is the signed version or the unsigned version. And I do want to double check and make sure that this is the unsigned version. So Intel mul instruction. Multiply instruction, Stack Overflow. Try not to do that. That's ECE 272. Okay, this is an AT&T rotation. Let's be more specific. Yep, right there. So we look up mul. Okay, imul is signed and mul is unsigned. So that is the right one to use because we don't want to use a signed multiplication when factorial can never go negative. Right? The factorial of the number should not be negative. Are we doing okay so far with the sample code at this point? So let me just bring the sample code back up again. Are there any questions before we assemble, link, and test run the program?
Is there any reason that you're using EBX and not just putting the literal value directly into the operand?
Because it is not supported.
Okay.
Okay, we can try that, but if I remember correctly, we cannot do an immediate operand with the mul instruction.
Okay.
But we'll give it a try. This is mul.o, mul.s, and that's why.
All right.
Yep. It's a very special instruction. It doesn't really fall into the same template as the subtraction, compare, or addition instructions. And I think this has to do with backward compatibility. It's probably back in the good old days when Intel or the X8086 or 8088 processor had multiply being a kind of special instruction. But this one we'll assemble, and then we'll link it to become the output of mult, like that. And then we'll test run it. All right. So it doesn't seem like. Is there any question I can answer? So, say again? Okay, well, it's all getting recorded, so let's go ahead and move on. Yeah, but it's going to disturb another student. Thank you. All right, so what we're going to do is to test this program and see what it does. Okay. I'm pretty sure the first three instructions are not mysterious at all. They're just move instructions. I'm setting up registers, EAX, EBX, and EDX to have specific content. So we'll go ahead and do a quick run through the first three instructions. So we'll put a breakpoint on the mul instruction itself on line 7. And then we'll run the program. At this point, I can do an IR, EAX, EBX, ECX, and EDX. And nothing is really surprising. EAX, the screen is off a little bit. I think it has to do with, well, there's an easy way to fix that. I can just move it a little bit like that. Okay, so this is not surprising because EAX is set up to be in decimal 1, 2, 3, 4. EBX is set up to be 5, 6, 7, 8 in decimal. And then EDX is set up to be ABCD, apparently for no good reasons. It's like, why do we even want to involve EDX in this case? So we'll go ahead and perform the multiplication next. So single step through the multiply instruction, and then we want to take a look at the registers again. Okay. The first part is not surprising. EAX is not outdated to a kind of pretty huge value. And that turns out to be 1,234 times 5,678. Okay, if you want to double check with the calculator, go ahead. EBX is not modified. Okay, it's just one of the numbers being multiplied, but the result is not stored in EBX. But one thing that's kind of surprising is what happened to EDX? EDX has a value of hexadecimal ABCD, which is kind of an arbitrary value that I want to store into EDX, but now it is 0. And that's because the multiply instruction, the mul long, the multiply long instruction, stores the product in 2 registers. EDX stores the most significant 32-bit of the multiplication, and EAX stores the least significant 32-bit of the product. So that's why EDX is also modified. Now you have to keep an eye on EDX, because if you were using EDX to store something useful during the execution of your program, and you execute a multiply instruction, EDX is going to be changed. Okay? So if you need EDX to preserve its value, you need to push it before the multiply instruction and then pop it after the multiply instruction. It is unlikely that you need to store that, okay? Because we are dealing with a 64-bit product here, and I only need you guys to work on a 32-bit number. Okay? Are there any questions about the multiply instruction? Yep.
Multiply EBX, why don't you just go EAX? Like, why do you okay, why don't you say like EAX or?
Because that's something I explained prior to your arrival.
Okay.
Yep. All right. So that's the first piece of the homework assignment that you need to know, is how to use the multiply instruction. Are there any questions about the multiply instruction? The implicit operand is EAX, then you have to specify only one more operand to complete the operation. So that's the first piece. Let's go back to factorial.s and take a look at, yep.
There's a problem with the homework.
Which one?
Factorial.
Yeah.
In the main.c, you're calling link, but there is no function named link.
Oh, okay.
Yeah.
Well, that will be a part of your homework assignment, is to change that reference.
Thanks.
Okay. The second part is, okay, so we got the multiplication part done. The second one is, how do we pass parameters? Okay, in the homework assignment that was due today, you only need to return a value, but you don't need to pass parameters to somebody else. In fact, you don't have to call another subroutine. So the question now is, how do we call a subroutine, call another subroutine, and pass a parameter to the other subroutine? Okay. So in order to demonstrate that one, I'm going to do this one. Okay, this is what I'll do. I am going to change main.c so that it implements another subroutine. It will implement another subroutine that returns an unsigned integer. We'll just call that Zelda. Hey, we got link, might as well. Okay, well, so we'll call this Zelda. And Zelda is going to take an unsigned integer, 32-bit integer, parameter, and we'll just call that, x4. Okay. And Zelda is going to return, x plus 2. Okay. It's not very exciting. It's just going to add 2 to the parameter x and return the value of that. Is that okay? So what I want to do is to change, quote unquote, my factorial subroutine to return what Zelda is returning to me. Okay, so I'm changing the nature of the program a little bit just to demonstrate how to get this to work. So we now have factorial returning, and you don't have to do these changes here because I would be testing your program through GDB, so I'm not even looking at the output of your program at all. Okay, so I'm changing factorial. I'm still passing 10 to it, but when I look at factorial, I'm changing the nature because I don't want you guys to think that this is what I'm implementing. So instead of this, I'm just going to do this. Okay, return the return value of Zelda of n. That's all I'm going to do. So the question is, how do I get this to work? In other words, factorial, in this case, not your homework actually has to implement the real factorial, but for demonstration purposes, this particular factorial doesn't do anything useful at all. All it's going to do is to call Zelda with the same parameter n. And whatever Zelda is returning, I'm going to return that too. Is that okay? All right. So the question is, how do we get this to work? Do you guys remember how we pass parameters to another subroutine? How do we pass parameters? On the stack. Very good. So this time factorial is the caller, and Zelda is the subroutine that we are calling. Okay? So I know that at some point we have to push the parameter. So I'll just say we'll push something on the stack. At some point we have to call the subroutine. We'll just say question marks here. And we know those instructions are necessary. So the question is, which one do I execute first? Do I push first or should I call first?
Push first.
I should push first because it doesn't make any sense at all to call first. If I call first, that means Zelda as a subroutine is going to get control already. And when Zelda has control, the parameter is still not pushed on the stack. So it makes sense that we have to push the parameter first, and then we call the subroutine so the subroutine can actually work with that parameter. Now, in your current homework assignment, I know most of you are not using the frame pointer, but starting from now, I want you guys to start to use EBP as a frame pointer. So now you have to set up the frame pointer just like what I talked about in the previous class. So I'm going to show you guys exactly how to do that one more time. Old EBP is 0 because EBP points to itself. So the symbolic name of old EBP is an offset of where EBP points to and what it means to be at that location. Are we doing okay so far with the meaning of the symbol? Okay? All right. And right before that, okay, is the return address, or I should say above that is the return address. It has to do with how we call the subroutine and how we set up ODBP. And then on top of that would be my own parameter. In this case, it is n. So n is return address plus 4. Inside the subroutine factorial, now I have to do it a little bit differently, because the first thing I'm going to do is to push EBP, and the last thing I want to do is to pop EBP, because they should be occurring in the same order. So I'm setting up the first part of factorial and the last part of factorial because I know I need to save the value of EBP, and then I can do whatever I want with EBP, and my caller would not be bothered because I'm going to restore the value of EBP before I get back to the caller. The second thing I want to do is to set up EBP to become my own frame pointer. So to do that, I have moved ESP to EBP so that EBP becomes a snapshot of the stack pointer right at this point of the execution of the program. After this point, I can now push as many things as I want to, but that won't change the offset to the parameter anymore. Are we still doing okay with this part? Okay. So that means at the end of the subroutine, I should have something that is reversing that. In other words, I'm moving the frame pointer back into the stack pointer. So this is helpful because I can push a lot of stuff in between and not pop them. And this one single instruction will restore and balance the stack without all the pops. Okay? So you can see that there's a symmetry between the beginning code, we call that the prologue of a subroutine, and also the ending of the subroutine, which we call the epilogue of a subroutine. You can see how they are kind of exact, but mirror images of each other. So in between, I can now specify whatever code I want to implement in between here. We want to call the subroutine called Zelda. Okay, so I know that at some point we have call Zelda as an instruction. But in order for Zelda to get the parameter, I also need to make sure that it's pushed on the stack first, so that Zelda as a subroutine will get n as a parameter. How do we do that? Would that work? Just push n. What is that going to push? Or what is that going to do when the program executes? Sorry? No. This is going to push whatever is at location 8 on the stack. And I probably do not have access to location 8 in the memory space. So what this will do is it will give me a segmentation fault, because that's not what I really want to do. Tell me again what is the meaning of label n in this definition. It's an offset to parameter n from not the ODBP, you're close.
Return address.
No. From where EBP itself is pointing at. Okay? Let me say that one more time. The labels OEBP, return address, and n are referring to the items on the stack. It's referring to the offset to those particular items on the stack from where EBP points to. Okay. If I have to draw a picture, to represent what is on the stack at this time, the caller to Factorial is going to push, n on the stack. So n is on the stack before the call instruction. The call instruction itself would push the return address on the stack. So in this case, n is the one with the higher address. Return address is the one with the lower address. After the call instruction, I will be inside the subroutine Factorial. The first thing I do in Factorial is a push instruction. I'm pushing EBP on the stack. So that's why old EBP is going to be here. So EBP from before the invocation of this subroutine is going to be here.
And why n doesn't work? It's shifted. Why did you say n call segmentation for?
Because, well,
It's shifted
okay.
exactly the.
Because that operand is not done yet. N is only a part of that operand. It's not the entire operand. Okay. So,
ESP
but
plus N.
let's finish this picture first, and then we'll go back to that. Now, after push OEBP, stack pointer will be ESP will be pointing here, right? Right after the push push L EBP instruction, ESP will be pointed at the last byte, the lowest byte of OEBP that is on the stack. And then what do I do right after the push L instruction? It's a simple move instruction, but what does that move instruction do? I'm copying which register to which register. I'm copying ESP to EBP. So if ESP is already pointing to this location, I'm just duplicating the same pointer or the same location and say that, oh, you know what? I also want EBP to be pointing to this location. Is that making any sense? So when you look at where EBP points to, it is pointing to its own old value. And that's why I label that as old EBP. 4 bytes away from where it points to is my return address, and 4 bytes away from the return address is my parameter n. And that's why, as an offset, n is 8. But 8 itself is not the address of the parameter. It is an offset from where EBP points to. So in order to actually push the value of parameter n, what do I have to do? Which operand do I need to use? This is a good starting point, but I need something else. In parentheses, EBP, exactly. So I'm using EBP as a base register. So this is basically saying, okay, EBP gets me close to what I want, but not quite exactly where I want it, because I want not what EBP points to, but 8 bytes away from where EBP points to, which is the parameter n that is pushed on the stack by the caller of this subroutine. Are we still doing okay so far? Okay. So this is a little bit more involved than what you have to do for the homework assignment that is due today, but this is also more universally usable because I can push any number of bytes on the stack after the move L ESP to EBP instruction, and it will not change the offset to any of the items on the stack at this point, because EBP does not change. Push only changes ESP, but not EBP. Are we doing okay so far at this point? Okay, so I push the parameter of n on the stack, I call Zelda, and then what do I have to do when Zelda returns? It seems like nothing, right? Because Zelda is going to return the value through EAX, and I'm going to return my own value through EAX also. So technically speaking, if I want to specify my return value, this is the instruction that I need to execute, right? Because EAX has the return value from Zelda, but you know what? That's exactly what I also want to return as my own return value. So, and that, by the way, is a valid instruction. It doesn't do anything useful, but it is valid. You can actually write it out, and it doesn't do a single thing. Okay? But it does emphasize the fact that I am reusing the return value from Zelda as my own return value. But this program is not going to run correctly. Okay, so what I'm going to do is I'm going to run this program so that you can see what happens when you miss certain things in writing a subroutine like this, or when you're invoking a subroutine. Okay? How many people want to kind of guess what will go wrong with this program?
It's no one.
Okay, it's going to cause a segmentation fault, and well, will it cause a segmentation fault? Actually, you know, I need to correct myself. It does not cause a segmentation fault. The stack is not balanced. It is poor programming practice, but I am saved by one of the instructions that I wrote earlier.
It's because the move on to the
Frame pointer into the ESP.
Yep,
So you
that
don't
is
have to pop anything.
exactly. So when you look at this code here, even though the stack is not balanced, after the moves L, EAX to EAX instruction, everything is going to be fine because of line 20. Okay, let's take a look at this picture again, okay? So this picture is still okay for the time being. This is current. This is reflecting the state of the registers and also the stack right after line 13 executes, right? Okay, so after line 13, we have line 15. Line 15 is going to push something here, which is really just an exact copy of n. So it's going to copy these 4 bytes over here, change ESP down here, and then we'll call subroutine Zelda. Is that okay? When we call subroutine Zelda, it's going to push a return address here, but that return address is not going to be important because when we come back from Zelda, Zelda is the subroutine that will make use of the return address. So when it comes back, ESP will now be pointing at the duplicate of parameter n again. Is that making any sense? Is that okay? All right. So that would be the state. So this is the state of the registers and also the stack. After, when we come back from Zelda, which means on line 18, this is going to be the state of the stack and the registers. And you can see that the stack pointer is not balanced. It is supposed to be back here, but it's not. And then we move on to line 20. What does line 20 do? It copies the frame pointer, which is EBP, to the stack pointer. The frame pointer is pointing at the right place already. So if I copy the frame pointer to the stack pointer, guess what? The stack pointer is going to point back to where it is supposed to be right before the pop L EBP instruction. Because what is the purpose of pop L EBP? It's not just to balance the stack. It is there to restore EBP because my own caller wants to restore the value of EBP. So now we're at exactly the right place to execute the instruction on line 21, which is pop L EBP. And then after that, we have a return after that, which is perfect because right after we pop L EBP, EBP will not be pointing here anymore, it will be pointing to someplace else. But then ESP will also be pointing at the return address, which is the exact place where we want it to be right before the return instruction.
So why segmentation fault?
So it won't cause a segmentation fault at all. It's just really bad programming practice because I'm not balancing the stack. But it won't cause a problem because I have the instruction on line 20. Now, if I did not have the instruction on line 20, then we have a problem.
So what you're saying is we should pop.
Yeah, we should pop anyway, because if I have a loop like this, it will chew up memory slowly, even though it's not going to cause a problem to have it right away. It will basically lead to the stack losing bytes for no particular reason. So it is a good idea to restore the space here by adding long 4 to ESP. In other words, whatever I use on the stack to push the parameter on the stack is useless after I come back from Zelda, because these 4 bytes, the only intention of these 4 bytes is acting as a parameter when I call Zelda. when Zelda returns, those 4 bytes are not useful anymore because Zelda is done already. Why do we want to keep those 4 bytes on the stack? Well, if we don't need those 4 bytes on the stack, we can just increase the stack pointer by 4 and reclaim that space and say, okay, it's the same thing as a pop, except we don't really care who gets the value of these 4 bytes because nobody needs to know these 4 bytes. And that's why we have an add long for $4 to ESP to restore the stack pointer after the call. Are we still doing okay so far in terms of just account? It's really just accounting, right? We are just accounting for the use of different bytes on the stack when we call a subroutine. Any questions? No questions? No one is remotely excited that we are using assembly language to call a subroutine in C and be able to get those to talk to each other properly? No one. It's just registers and stack and offsets of some kind. Okay, so yeah, go ahead.
The add long or to ESP, is that optional or?
That's a tricky question. It is, without the instruction on line 17, the program is not going to crash, but you'll be wasting 4 bytes on the stack for no particular reason. So it's a tricky question to answer. It's not going to cause your program to crash, but yet you're not using the space on the stack efficiently either. Okay. Now, if that is stuck in a loop, if I'm calling Zelda in a loop, it's not going to cause anything to crash either, but you'll be chewing up space on the stack because every time you allocate space for the parameter, you're not reclaiming that space once that space becomes useless. So that's why we want to kind of make a good habit out of this and make sure that we reclaim the space on the stack when it is not needed anymore. Any questions before we give it a spin and see if it works? Okay, questions? Okay, if there are no questions, we'll go ahead and give it a spin and see if it works. So in this case, you can see that Factorial is nothing more than a relay of Zelda. Calling Factorial is the same thing as calling Zelda. So we'll go ahead and see if it works. Okay, we make. And it's complaining, it's a warning of implicit declaration of function factorial. That's because in main, I did not make a prototype of factorial. I have the prototype of link, which is useless at this point. Okay, so we just need to change it to factorial. Now the compiler is happy, the linker is happy. According to the program main, what should it print? Factorial returns what? What should it return? It should. It's not going to return Zelda. Okay, Factorial is nothing more than a relay of Zelda. So in other words, when I call Factorial, all it does is to say, I don't know what to do. I'm going to ask Zelda, and Zelda says, I'm going to return, whatever you pass to me plus 2. So that means, the program should print 12. Okay, it should print Factorial returns 12 in this case. Okay, so we'll take a look and see if that's the way it's going to work. Okay, /main, and it returns 12. Okay. Are there any questions about this particular program? Because this is the second piece of information that you need for your homework assignment. Is how do we set up the stack so that we can call another subroutine? Is that okay? Oh, then you have all the pieces already. Yep.
The question is, though, does that have to be done every time you call that subroutine?
Does what have to be done every single time?
Like, so let's just say Zelda called Factorial.
Okay.
Would you have to do that same setup every time?
If Zelda calls Factorial, then Zelda, the caller, is responsible to push the parameter on the stack before it calls Factorial.
So that means if the caller and the call heap, so to speak, are the same thing, then
It doesn't change a single thing because
it's the same process.
it's the same process.
Okay.
How we pass parameters to a subroutine does not matter whether it is recursive or non-recursive. Every time you want to call a subroutine with a parameter, you push the parameter on the stack, then you call the subroutine. When the subroutine returns, you reclaim the space that you have used up for the parameter, because nobody cares about those values anymore. So you have to reclaim that space by adding a number to the stack pointer. And that is independent of whether it is recursive or not. Any other questions about this particular homework assignment?
If Factorial is calling Factorial, how do you eventually get it to stop? Yeah.
Well, that's a good question. You know, that's a clear indication that you did not take cisp310 from me, which is fine, because in cisp310 the way I taught it was, as soon as I got into subroutines, I introduced the concept of recursion. So, but that's a very good question. Let me. I was trying. Oh, okay, go ahead. Let me pop the code back up again, and so you can take a look at it.
In recursive subroutine, like whatever the base case is reached is when it stops.
Yeah.
So the base case in that subroutine is, as long as n is greater than 0, then it's going to continue to call Factorial. Once n equals 0, it's going to go to the second part of the unary condition statement, which is just returning 1.
Okay.
And then it will propagate back. That's how all recursion works.
Or the other way, for a more tedious way to write the same subroutine is like this. Let me just give you the alternative way to look at the Factorial, even though it's still using the recursive definition. In this case, it's u in 32 because I'm using mole and not imole. Okay, so here's the other way to look at the same subroutine. I'm just going to be lazy and not use the pound. I'm going to re-add the pound later. So the other way to look at this is to basically say if n is greater than 0, then we want to perform this block, else we want to perform this block. But what this block is going to do is simply to return n times the factorial of n minus 1. And then the other block, which is here, is returning a value of 1. So to answer your question of when do we stop, we stop when n is no longer greater than 0. Now how do we know that's going to happen eventually? Well, every time we call Factorial from inside Factorial itself, we are not passing n along, but we are passing n minus 1 along. So every time we perform that call, every time we stack up another call, the parameter is 1 less than the prior invocation.
Okay.
And that's why I can start with, let's say, 1,000, but the next time it calls itself, n is going to be 999, 998, and so on. So eventually it will get down to 0. And when n is 0, it is no longer greater than 0, which means we'll get to the else case, and we'll just simply return a 1. But that will return to the factorial invocation of the previous level, and it will just use that value for the multiplication, and then itself it will return again, and it will go back to the previous one, and so on. The reason why I like to use Factorial when we talk about subroutine invocation is if someone can work with subroutine invocation without recursion, but not when it is recursive, that tells me something. It tells me that person does not fully understand the concept of subroutine invocation, because the mechanism of calling a subroutine and also returning from a subroutine does not matter at all whether it is recursive or not. So if someone has a problem understanding when it's recursive, but not a problem when it is non-recursive, that means that person has some kind of a misunderstanding of the mechanism of calling and returning from a subroutine. And that's why it's a really good test to see if, whether the concept itself is well understood or not. Any other additional question about the homework assignment? No other questions about the homework assignment? Do you see any local variables used in this case? Yep, go ahead.
I saw the move L EX to EX. What was that supposed to do?
Nothing?
Nothing.
It doesn't do anything because of the way I modify the meaning of factorial. But in your factorial, you cannot use, you don't want to use just, move L, EAX to EAX. The only reason why I put that here is because after I change the meaning of factorial, I'm just returning whatever Zelda returns to me. So it's EAX to EAX. Remember, EAX is still the register that you use to return the value of this particular subroutine. Okay, so that is the most important part to remember. All right. Yep.
We are still not modifying main, correct?
You don't have to, well, you do have to modify main because you don't have link to call anymore. So you do have to fix that so that the compiler and the linker does not complain.
Other than that,
Yeah, other than that, you don't have to do anything to main. You just have to make it compile.
and what should be the output of the assembly code?
What should be the output of the factorial of 10? Well, the factorial of 10 is 10 times 9 times 8 times 7 and so on. And if I want to find out what it is,
450360. Oh, 3600.
okay. Well, I'm going to cheat.
3,628,000.
Yep, I use a spreadsheet as if it's a calculator. Because it is a calculator. It's just a very complex and useful calculator. Right? So are we still doing okay so far with this? Okay? So once we are done with this one, we can now move on. So we have just talked about how to set up the frame pointer, which is EBP. We know how to set it up so that we can use the frame pointer to access my parameters. What we have not really talked about in details, we kind of talked about this last time, is how do we use local variables. So that's the next topic, is to talk about how do we make use of local variables. Right? So what I'll do is I'm going to give myself more programming assignments. Okay. So I'm gonna. There's no need to save that one. So I'm gonna use local var as a folder, and I put all the sample programs related to local variables here. Okay. So I'll go ahead and make one C program, and then I'll turn it into assembly language. So we'll go ahead and take a look at. Let's see. Well, we might as well do the whole thing here. So I'm going to copy my factorial makefile here, just so that I have a makefile to help me with all the other stuff. Okay, so we'll deal with the main file first, and we'll define a particular function or subroutine that makes use of a local variable. And this one's going to be fairly simple. I'm just going to define f as a subroutine. It has no parameters whatsoever, but it has a local variable, and the local variable has a type of unsigned int, 32-bit. We'll just call that I. And inside f, I want to initialize I to 0. As long as I is less than 32, we will perform the loop here. And after each iteration, I'm going to increase I by 1. And inside the loop here, the only thing I want to do is to print the value of I, using standard out. So it's printf %u to print something in the unsigned format, and then we have the line feed character, and then I give you the value of I to print, and that's my subroutine here. And then I'll define my main subroutine, which does not take any parameters. The only thing it's going to do is to call f and then return the 0. That's my entire program written in C, C++, whichever way you want to look at it. Okay. Any questions about this particular program? Any questions? Okay. So can anyone tell me what this program is going to do? If I just run this program outside of GDB by itself, what is the observable outcome of this program? It prints 0, 1, 2, 3, 0, line feed, 1, line feed, and so on, until it prints 9 line feed, and then it gets out. So it prints 0 to 9. It doesn't print, it prints all the way up to 31. Okay, I forgot that 32 is the boundary. So it prints 0 all the way up to 31, and each time it prints a number, it will also print a line key character, so that the next number starts with whatever line that is following. Okay, so let's double check and make sure that is the case. And I'll change my makefile, so it doesn't have a assembly language file anymore. It doesn't have anything that ends with .s. And that's all I need to do to change the makefile to make it work with this case. Okay. So make, and it says, okay, that's because I forgot to do the pound include stuff. Pound include standard io.h, pound include stdint standard integer.h. So those are the header files that have to include in order for uint32_t to have a meaning, and also for printf to have its prototype. This will make the compiler happy, and also the linker happy. Yep. Okay. And then we run the program. It prints every number up to 31, and it terminates. Not very exciting kind of program. Okay. But the exciting part is, how do I change this program or the subroutine f and implement it in assembly? Okay, it doesn't have a parameter, so it doesn't have anything to do with parameters, which we should understand really well at this point already. Okay, are there any questions about what I am about to do? I'm about to change f into the assembly version, but keeping everything the same. Okay, I'm going to keep the meaning of the subroutine exactly the same. It's going to do exactly the same thing. It will call printf, okay, exactly the same way as the original C code. Okay. All right. So let's go ahead and take a look at how to do that. The first thing I need to do is to comment out the definition of f here, because if I'm redefining f in assembly, I don't need it to be here. Okay, so I'm going to comment out the entire definition of subroutine f. And the trick that I usually use to do this is basically just to say pound if 0, and then end if at the end, pound end if. I'm using the preprocessor to help me cut out a major portion of this particular program. Okay. I still need one little thing here. I need the prototype of f, just so that the compiler is happy, because it understands that f does not take any parameters, it does not return anything. The second thing after this I need to do is, this is line 5 to line 13. So 5 to line 13, yank, which is the same thing as copy. I use a new file called f.uppercase_s. That's the source file in assembly. And then I do a paste here. So I'm just copying and pasting between the C source code and the assembly source code. In the assembly source code, this part should not be assembled because it's not assembly instruction. So what I'll do is I'm going to put pound ahead of to the left hand side of every single line, so they're all commented out. The reason why I need pound instead of a single pound is if the subroutine has the word if, then it becomes pound if, and then the preprocessor will kick in and go, oh, you mean pound if? No, I don't really mean pound if. It is just commented if. So pound will basically get around that problem, because it's no longer just a pound followed by an if. And then we do all the other stuff, the usual stuff, which is .global. Whatever label we want to export, we want to say .global, and then that label, in this case, is just f. And then we have the entry point of the subroutine here, and then the exit point of the subroutine here by a single return. So you can see that when I write programs like this, I'm not writing the program in any sequential manner. I start, and then I go to the end, and then I go into the subroutine, and I can continue with that. It doesn't have any parameters, but I still have other stuff on the stack that I need to keep track of. That means it is probably still helpful for me to keep track of the offset to old EBP from where EBP points to. It is at 0 offset because EBP is pointing to its own old value. The return address is not really helpful in this case at all, because we don't have any parameters, but I'm still going to define it anyway, just so that I know where the return address is. But from the other side, the negative side, I have something that is useful. I have my local variable I, which is below OEBP. So it's OEBP -4, because it's going to take up 4 bytes. So if we take a look at what the stack looks like when f is called, we have a return address which is put here by the caller of f, okay, which is of no interest to me as a subroutine at all. Okay? And then the next thing I want to do is to push EBP. So EBP, or the old value of EBP, is going to be right below the return address. Right at this time, I take a snapshot so that at this point, ESP and EBP will both be pointing to this location. But I also have a local variable. I cannot put my local variable anywhere before this point, but I can put it after. In other words, I'm going to allocate the next 4 bytes for my local variable I. Now, in order to do that, in order to allocate these 4 bytes for my local variable I don't want to change EBP, but I can certainly change ESP. So I can basically just say, oh, adjust ESP so that it is now pointing to the last thing that we allocate from the stack. Are we still doing okay so far in terms of what I intend to do from the call frames perspective? Is that okay? Okay. So let's go ahead and add the code, what we need to do here. So we go into the subroutine. The first thing we have to do is to push EBP. And then to counter that, we have the matching instruction of pop EBP at the end. And once again, you can see that I do not write my program in a sequential manner, because when I push something, I know eventually I need to pop it. So I want to specify the pop instruction as soon as I specify the push instruction so that I don't forget it. Okay. The next thing I need to do is to take a snapshot of the stack pointer. So I moved ESP to EBP so that the frame pointer becomes useful at this point. And then I have a matching instruction at the end to basically say, okay, let's put the frame pointer back into the stack pointer before we pop its own old value back. Okay. And then after that, I have one more thing to do this time that I did not have to do last time. Because this time, I also need to allocate 4 additional bytes below where EBP points to, because that's for my local variable I. Now, I know in this particular program, I really don't need to have a local variable, but I'm going to I will make my assembly code resemble the C code as much as possible. So in this case, how do I reserve those 4 bytes? Go ahead. We can subtract, exactly. So we can basically either use subtract long, and how many bytes should I subtract from the stack pointer? 4 bytes. Okay, I can subtract more, but 4 is all that I need. So I'm going to subtract 4 from ESP, and that will reserve space for my local variable I. Okay. Technically, I really should do an add long 4 here, but it's not really needed because when I perform the move instruction, it will restore the stack pointer to the right place anyway. All right. So we are pretty much done. Oh, I just realized that I was using the wrong part of the instruction. So this is the proper interleaving of the code. So now I'm ready to execute this part, or specify this part of the subroutine, which is a for loop, and inside the for loop I need to call printf, change I, and so on. Any for loop is basically a while loop. In other words, I get 0 is something that we have to do before we get into the loop. I is less than 32 is the condition of the while loop. And then plus I is what we need to do at the end of each iteration before we go back to reevaluate the condition. So that means we can specify the initialization here first, because it only needs to be done once. How do we initialize my local variable I? How many instructions do I need? One instruction. And what would be the operands to that instruction? $0, very good. Okay. Right? Because I is, as a label, I is defining the offset of my local variable I from where EBP points to. The based addressing mode is perfect for this purpose. Okay? So this instruction will basically say I get 0 in C. And then at this point, I can begin my while loop. So I put a label here, begin while. But as soon as I do that, I also know that at some point I have to go back to begin while at the end of this loop. So I jump unconditionally branch back to begin while at the end of the loop. And because I know this loop is going to exit at some point, I also have end while defined right after the unconditional branch. In other words, I'm writing my program, but not in a linear way. I'm writing the program in a way to resemble the structure. I'm going from the outside to the inside. At the beginning part of the while loop, I need to check the condition to see whether I is less than 32. If it is not less than 32, I need to get out. Okay? So what do we need to do? How many instructions do I need to specify if I is not less than 32, we need to get out?
Compare.
Two instructions? Okay, so we have a compare long and a jump. Okay, so we have a compare long and a conditional branch instruction to end while.
Jesse,
No, not less than.
oh no, that's not.
Jump if not less than, and in this case I is unsigned, so jump if not less than is jump if not below. So we are comparing I to 32, so we have 32 here, and we specify I EBP over here. So that is going to compare I to 32, and will branch to end while when I is not below 32 anymore. Are we doing okay so far with those instructions? Do you guys remember how to read the compare followed by a conditional branch instruction? I'm just gonna I'm gonna point to it just to remind you guys how to read it. So the way you read this is you say jump to end while if and only if this operand is related to the other operand using these words and then the other operand. So in this case, we are jumping to end while if and only if I is not below 32. Okay, it's kind of like an awkward order to read it, but once you get used to it, it's really, really helpful. So now we have taken care of the condition part. We also know that before we branch back to the beginning of each loop, we have to add 1 to I. How many instructions do I need to add 1 to I as a local variable? Yep, just one instruction. Add long $1 to I in parentheses EBP. Okay, not ESP because we want to leave the stack pointer alone, at this point. All right, so we have the structure of the loop set up already. Now we just have to specify the printf instruction. Can we really do that in assembly? Can we actually call printf in assembly? Sure. Yeah, exactly. That is the right question. Why not? Okay, because we already know how to call any subroutine. When you call subroutine, we are pushing. Okay, so let me ask you guys this. Okay, since someone said why not. When you have multiple parameters to a subroutine to call a subroutine, which one do we push first? In this case, let's just look at this particular example. Which one do we push first? Yep, we push I first and then the address of the string. Okay, so we'll push I first. So pushing I is easy because we just have to say push I EBP. Now remember, we are pushing the value of parameter of local variable I and not the address of local variable I, so this would be the correct operand. What about that string, %u \n? How do we push that on the stack? Well, it's not as easy. That one requires just a little bit more code because we have to specify the printf, format string. I'll just have to define another label for that purpose, and it is .ASCII, okay, ending with a z because it is a no terminated string. But within the string, I can now specify exactly what I need to specify in it. It's just %u with line feed, and I think \n is recognized in assembly as well. I guess we'll know soon enough whether it is or not. So now we have to push L, the label of that particular string, which is printf format. Now that we have pushed both of those on the stack, we can call the subroutine called printf. And is there anything else we need to do in this program so that it is not wasteful? It is not going to crash, even as it is now, but it's going to. This is a little bit wasteful. Why is it wasteful?
We're returning the 4 bytes back.
There are more than 4 bytes. There are 8 bytes, exactly. So the 8 bytes that we set up, as parameters to printf is not reclaimed, as it is now. So we want to reclaim those 8 bytes because we don't want to waste space on the stack. So the way to reclaim those 8 bytes is not.
Can we do like 8? Or we can do 4 and 4?
Well, we just do an add long 8 to ESP. We just push. Basically we are quote unquote popping, but we are not. Nobody needs to get those 8 bytes. So we are just adjusting the stack pointer to point back up, 8 bytes to reclaim that space. All right. So I think we are done. Yep.
You're calling the printf. What is printf defined by
The linker will take care of it.
So we already have printf in our system?
Yeah, the linker will take care of this because printf is a part of libc, which is a library that is usually linked with a C program.
Oh, so printf is a calling system. The printf is something there.
Printf is a label that is defined in the library that is typically linked with C program. So we don't have to specify anything special for that to be linked. There's a whole bunch of stuff that is part of the quote-unquote standard library, but certain things are not. Like I think sine and cosine are not. Those things you need to specify. I think dash math or dash math or something like that. Yep. All right. So I think this is all done. So we'll go ahead and change the make file first because the make file is not aware of the assembly file. So we need to make the make file aware of that first. So we have to say, okay, there is one source file, specified in assembly, and it is lowercase f dot uppercase s. Now the significance of the uppercase s is not going to be useful at this point, but when we have to include files for our assembly code, then it becomes useful, okay? Because we can actually do a pound include in assembly code, okay? And we're not quite there yet because at some point we're going to deal with structures. So we'll deal with structs in assembly language. Not only all the usual stuff that we deal with in C and C++, but also structures. So we'll deal with this program first and give it a try. Any complaints about line f.s, line 8, end of line has a 3. Okay, so we'll go ahead and take a look at f.s on line 8. Which line is it complaining about? It's line 8. First unrecognized letter is 3.
Should we double click?
Yeah, I would say that's probably the first thing to check. Yep, that's it. All right, so is it gonna work? Dun, dun, dun. And it does. Yeah. So are there any questions about this program? Well, we have another 8 minutes left. I think we can do pointers.
Just go to the lab.
No. We got to do pointers so that pointers will become a part of the next homework assignment. Okay, so let's take. It's not as difficult. It's not really as bad as it seems. Okay, so we'll go ahead and we'll take a look at main again, and this time we'll change f a little bit. So we'll go to. Okay, we'll change this version first, and then we'll go ahead and instead of using ++i, I'm going to call a subroutine to do that. Okay, so I'm going to call a subroutine called let's say increment. And I will pass the address of I to increment. And then increment is going to be defined here as void. It doesn't return anything. And the only thing it needs to do, or it will take one parameter, which is uint32_t. It is a pointer to an unsigned integer, 32-bit. So we'll just call this pointer, ptr. And what this is going to do is to increment whatever the pointer points to. Okay? That's a fairly, it's a C thing, okay? You just have to look at this construct from the inside out, from the parentheses perspective. So we have, asterisk PTR first, which means we are dereferencing the pointer first. And then we have the pre-increment outside, which means we are adding 1 to whatever the pointer points to, which is just adding 1, right?
Before the executes, right?
Sorry?
Before it executes, though.
Before
it executes, if the number was given was 1, so before it executes, the program will already be 2, right?
The PTR is pointing to a location that has a value of 1. This will add it to 2.
Before it executes.
Doesn't matter because it has no return value.
Oh.
Just to make sure I'm clear, you have to dereference the pointer first because pointer arithmetic is done from right to left instead of from left to right. It reads operations from right to left. So it has to be inside parentheses.
I just want to add the parentheses to make it very clear, is the increment happening first or the dereferencing happening first. So this way it's not ambiguous. We are definitely dereferencing first, and then we are adding 1 to whatever the PTR points to. Okay? So the first thing we do with this program is not to implement increment in assembly, but to change my assembly version to call INC. Okay, that's the first thing we need to do. So let me split the screen first so that we can refer to both code at the same time. Yes, VI can do this. Very nice. All right, so now we have the modified version of F, and I have to go to subroutine F to change it. So instead of using a very simple instruction like this one, I'm now changing this to do something that is a lot more complicated to accomplish exactly the same thing. In other words, I want to add 1 to local variable I, but instead of using add long, I need to do the whole complicated thing of passing the address of local variable I to INC as a subroutine.
Why?
Yep.
Why do I feel like this is like, instead of buying gas for your car, strapping rockets on top of it and shooting it?
Because my motto is if there is a harder way to do something, let's do it that way.
Because it's slow.
Okay. Okay, so this is important because this is the first time we actually see how an address of a local variable is passed. Okay? So we know certain things is for sure. We know that we have a parameter to push on the stack. We know that we have to call INC as a subroutine. We also know that we should clean up after ourselves by adding 4 to the parameter or the space that is used up by the parameter. So we know kind of the structure of this thing here. The question is, what am I really pushing on the stack? The obvious answer is the wrong answer. Because the obvious answer is to say, oh, we'll just, I've seen that many times, it must be that. Nope. Because what this is going to do is to push the value of local variable I on the stack. I don't want the value of local variable I. I want the address of local variable I. So how do I get the address of local variable I on the stack? $sign is not going to work because it is not a valid syntax. I cannot do this either.
Where is this?
It cannot be done with one single instruction. How about that? Okay, it cannot be done with one single instruction. I can do that in 2. Yep.
Do you need to copy the value of I to a register and then use the register to push the register to the indirect of the EBP?
Okay, that would be the more direct way to do it. Okay. Okay, so what I'm going to do, okay, I will start with this instruction. I'm pushing EBP on the stack. How close am I at this point? In other words, EBP is the address of ODBP, right? So how close is the address of ODBP compared to the address of local variable I? Pretty close, right? I mean, we are almost there. So what do I need to do with the number that I just pushed on the stack to adjust it so that, I don't really mean here, I really meant here. Subtract 4, okay? But I don't want to deal with the literal constant 4. I want to use the label name I. So what do I use? how do I make use of I in this case? How about this? Add long I, $I, to whatever the stack pointer is pointing at. Would that work? What is I? Is I positive or negative? I is negative. Because it's OEBP minus 4. OEBP is 0.
But if we define it for ODB minus 4.
That's how we defined it earlier.
So at that point.
So if you're adding a negative number, you're subtracting something, right? So this should work, okay? So remember the reasoning, the rationale of this is EBP as a pointer is getting us pretty close to the address of the local variable. We just have to tweak it a little bit so that it actually points to the local variable. So the first thing I do is to push EBP on the stack, and then I just say, oh, you know what? That thing that we just pushed on the stack, let's tweak it. And the tweaking is done by the add long instruction. So let me go back to the add long instruction here. So the add long instruction is adding I immediate to whatever we just pushed on the stack, because the stack pointer always points to the very last thing that we push on the stack. And we just push the register EBP on the stack. Okay, so we are just tweaking it. So we're basically saying we're pushing another thing. Okay, if you want to look at the picture here, this is I, and then we just push EBP first on the stack. EBP or whatever we push here is pointing to this location, and we say nope, that's not the right place to point to. We want you to point to here. So we just have to say, oh, let's go ahead and just add -4 to this thing, so now it's pointing 4 bytes down from where it points to before.
This is all, to me, reminds me of assigning pointers to other pointers.
Assigning pointers to other pointers.
Like when you take, like, say you want a pointer that's pointing to one value, and you want to make another pointer point to that value by using the pointer itself.
Well, it is pointer arithmetics.
Yeah, that's what I'm getting at.
Yep.
How do you get to this value? Why don't you define I to be at that value right there? But when you come to this stack like EBP plus minus 4, when you come here?
I push EBP first, so initially it points to here, and then I subtract 4 from these 4 bytes, so it points to 4 bytes below.
But when you initially pushed, so you pushed the EBP after you pushed I there? So EBP was.
I push EBP and then adjust what I push on the stack. I don't want to do any arithmetics on EBP itself, because EBP is always going to be pointing here. I don't want it to move at all. But I can change a copy of EBP once I push it on the stack. Okay, I know we are running out of time, but we want to see whether this works or not, don't we? Nobody cares. It's like, yeah, whatever. And it does.
Before you stop recording, I want to go on record as saying I hate pointer arithmetic. I hate pointer arithmetic.
Oh, from here on, it's all going to be pointer arithmetic, and it's going to get worse because we'll deal with structs. So we'll get to the address of a particular member inside a struct that is pointed to by another pointer.
The rest of you will deal with structs.
Okay. Well, I'm hoping that this will give you a preview of what the next homework assignment will be about.
Yes. I love that.